Okay, everyone. So, last week we finished the control design, PID control design, and Laplace domain analysis of the dynamic system. And we also briefly talked about the system description in state space. Any question in terms of the state space formulation? It was clear to everyone?
Would we do another example?
Yeah, I will do some examples today as well. Okay. Today, I will talk about what's the relation between the block diagram and state space formulation, and also about analysis of the state equations, how the state space and the Laplace domain are connected, and how we can transform the system representation in state space form to Laplace domain, or from Laplace domain to state space form. Okay. The most effective way to show the effectiveness of state space performance is using this state variable equation in implementation of this state space formulation in analog system. I think analog system is out of date nowadays. Nobody uses the analog systems. Now everything has been digitalized. But it's good to know how analog system and control system works in terms of state space formulation. The main structure of the state space formulation is integration. As we discussed, we transform higher order differential equation to first order differential equations. Everybody knows how to solve the first order differential equations, linear differential equations. If even we have nonlinear differential equations, it is much easier to have first order differential equation rather than having higher order differential equations. We explained how we can transform the states, how we can define the states and transform from the higher order differential equations to first order differential equation through some examples. Today I will give you more examples as well. In reality, the analog computers are the system composed of electric components designed specifically for simulate ordinary differential equations. The main purpose of using computers is to analyze differential equations which represents dynamic response of the system. Okay, somehow. Any software you use, not CATIA, MATLAB, Adams, whatsoever you use, you want to build up a virtual system in order to analyze the performance of the system subject to different inputs and disturbances whatsoever. So analog systems have been designed such that simulate ordinary differential equations or equation of motions of a dynamic system. As I said, the basic dynamic components of the analog computer is an integrator, which is constructed or built up using a capacitor and a resistor and amplifier, operational amplifier. What's the operational amplifier? What's the integrator? How it works? If you are or if you are interested, you can learn in a mechatronic module. But today I won't give that much detail. Just to give you an idea, here is the circuit that integrates the voltage. If you have a resistor in the feed-forward path, and one op-amp, and one feedback, and capacitor, if the input voltage is, for example, sinusoid, the output will be cosine voltage. This is the integrator, which we represent by the block diagram as 1 over S. X dot is the input, X is output. Okay, so there are something real that do this integration. This whole circuit can be shown by 1 over S. We have the mechanical integrator as well, or differentiator. A damper can be a mechanical differentiator, or a spring can be kind of the integrator. It depends how you define the relation. But we have mechanical integrator or mechanical differentiator or electrical integrator like this or electrical differentiator. What's the mechanical integrator or electrical integrator or differentiator or op-amp system? You will learn in mechatronics module if you would like to take it. But I won't go to details of the system. Again, let's give you an example about the state space formulation, and I would like to show the basic interconnection between a Laplace domain and state space using an example, through an example. Assume we have this third order differential equation which represents motion of a dynamic system. Usually, as a mechanical system, the highest order differential you can get is what? Which order of differential you will have? What?
Second order.
Second order. Why? Why this is the second order, the highest order you get?
The acceleration.
Yeah.
Exactly.
Newton's law.
Because you use the Newtonian law. And the Newtonian law is based on the acceleration, which is the second order differentiation. Okay? But assume you have such a system, it can be hydraulic system or thermal system, which its dynamic can be shown by third order system. So we have one input, and here's the dynamic of the system. First, I want to show how to build up the state space formulation and how to connect or transfer this state space formulation to the Laplace domain. In order to build up the state space, I keep the highest order differentiation in the left side and take the rest of the elements in the right side. Okay? This is the highest order of differentiation, and the rest is in the right side. Then, if I want to show based on the block diagram, look, I can show the block diagram as this one, or state space. Y triple dot goes to the 1 over S, build up the Y double dot, goes to 1 over S, makes Y dot, and goes to 1 over S again, makes Y, which is usually we look for. We want to analyze the response of the system, position, displacement, whatsoever. So, according to this one, and considering in our mind that the mass element is integrator, I can define the proper state space. From last week, what can be the best selection of the state variables for this system? If we choose integration, I can choose x1 as y double dot, x2 as y dot, and x3 as y. So, okay, I will explain. But keep in your mind, I can choose the best way of choosing state variables because the output of each integrator can be my state. Okay? As I said, the main advantage of state space representation is that we use integrator and convert higher order differentiation to first order differentiation. How I will explain here. Look, I define, if you look at it this way, again, let's get back here. I define x1 as y double dot, x2 as y dot, and x3 as y. x1, y double dot, x2, y dot, x3, y. If I choose my state like this, x dot 2 is equal to x1, isn't it? What's the x dot 2 is y double dot. And if you look at here, y double dot is x1. X dot 3 is equal to x2. Correct? And x dot 1 is a y double dot, which I have this relation here. Look, x dot 1 is minus 6 y double dot minus 11 y dot minus 6y plus 6u. What's the y double dot? y double dot is x1. So x dot 1 is minus 6 x1 minus 11 y dot is x2 minus 6 x3 plus 6u. I have x dot 2 equal to x1 and x dot 3 equal to x2. Look here. Instead of having one third order differential equation, I have first order differential equation. So I converted this third order differential equation to 3 first order differential equation. Solving such differential equation is much easier compared to solving the third order differential equations. How can we solve this set of the differential equation? I will explain today. Okay? Any question? Okay, so how can we connect this, represent this one, the STS in the Laplace domain? Again, look at the block diagram we have. The highest order is y triple dot. And I need 3 integrators to get to y. I defined my states, the output of each state, output of each integrator as my state. I have 3 integrators, so I need 3 states, and the output of each integrator is my state. The purpose I want to show you, I want to build up this differential equation, the main one, using block diagram. So the first element of this differential equation, x dot 1 or y 3 double dot, is u. Look, u is the input, multiplied to 6, 6u plus something will give you y triple dot. To make the whole y triple dot, I need to build up these 3 elements as well. So I need to take feedback from each integrator. Is that clear to everyone?
Yes.
Okay. So look, I have minus 6x1, minus 11x2, minus 6x3. So y triple dot is minus 6y double dot, minus 11y dot, minus 6y, plus 6u. So you build up the main differential equation using this one. This is the structure you need to use in reality to have this differential equation in computer. Okay? So any question?
What about sign of flow diagrams?
Is all positive because I included minus, minus, minus here. Is all positive summation. Okay. So I want to see based using that block diagram and STD space I define how can I build up the STD space formulation. If you look at here, using the state I defined, the matrix, the state vector is x1, x2, x3. I have 3 differential equations. So in the matrix format or vector format, I have x dot 1, x dot 2, x dot 3 equal to where's the eraser? Have you seen eraser somewhere? Patrick was erasing.
What is that thing over there? That who's that?
No, it's umbrella. Oh, do you have tissue? I don't have tissue. Patrick put it here. Okay, forget all it. that? Yeah. Okay, so let me continue here.
Yeah.
I have x dot 1, x dot 2, x dot 3 equal a matrix multiplied to x1, x2, x3 plus a vector multiplied to input u. X dot 1 is equal to x dot 1 is equal to x2, isn't it? X dot 1 is equal to this minus 6 x1 minus 11 x2 minus 6 x3. X dot 2 is equal to x dot 2 is equal to x1. So 1, 0, 0, 0, 0, 0, 1, 0. X dot 3 is equal to x2. But x dot 1 is a function of input u as well, which is 6. But x dot 2 and x dot 3 are not function of u. So x dot 1 is equal to this matrix multiplied to system matrix multiplied to state vector plus input vector multiplied to input. And the output is y, which is y is equal to x3, x3. So y will be 0, 0, 1, x1, x2, x3 plus 0u. So here is the representation of that block diagram. But if you have these matrices, you can use MATLAB to get the transfer function, the related or equivalent transfer function. How can you use? You need to use command state space ss2 transfer function, tf. ss2 tf gives you a numerator and denominator of the transfer function, the equivalent transfer function. If you give matrix F, G, H, J, given here, you will get the numerator and denominator of the transfer function. So in coursework, your coursework, if you have, look, you have many ways to justify your calculation and hand design. You can define the state space, you can define the state variables, find the matrix F, G, H, and J from the equations of motion. But in part 1, you calculated it, or in second part, in third part 3, you will need to calculate the transfer function. If you have the state space representation, you can use this state, but first you need to do by hand. Okay? The calculation you need to do by hand to find the transfer function Zs over Zr. To justify and prove the correctness of your answer, you can use the MATLAB command std to transfer function to show that your hand calculation is correct. Is that clear? Okay. But using this system, I will explain to you how to find the poles of the system. But before going further, if you would like to see the location of poles and zeros of this state space transfer function, state space representation, you need to use the state space to zero pole command. Yes.
Can you just explain where you got y out of that?
What's y here? x3 is y. 0 to x1, 0. 0 to x2, 0. 1 to x3 is x3. Okay? If you want to find the pole and zero locations of this state space representation, you can define a vector z, pk, 0 poles and gain k. State space to 0 pole. Zp is the abbreviative for 0 pole. F, G, H, J, which F, G, H, A are given here. Okay? Or if you have transfer function, you can use ZPK transfer function to 0 pole. Numerator and denominator. If you have a transfer function, you can use this command TF to ZP to find the poles and zeros of your system. How did you calculate the pole location of your fourth order system? You use MATLAB, root command, yeah? Or you can use this TF to ZP to find the zero pole locations of your transfer function. But it's the same. Okay, if you use this, either of these commands, you will get Z0 because there is no zero. Poles located as -3, -2, and -1, and gain 6. Okay, any question? Yes?
Just what does this one? SNS is state space?
STD is abbreviated for STD space. TF is abbreviated for the transfer function. SS is abbreviated for the STD. Okay. So, in the fraction factorized format, ys over us will be 6 over s plus 1, s plus 2, s plus 3. Okay. So, what I gave you so far, it was introduction. Now we go to the main step, how to find the connection between STD space and transfer function. Look, we have two situations. One, STD space representation is given and we want to transfer it to the Laplace domain, or find the Laplace transfer function, or Laplace transfer function is given and we want to find STD space representation. Okay, we have two situations. First, I would like to talk if a transfer function is given, how to find the STD space representation of a dynamic system. To show that, I will explain through an example. We want to see what's the relation between block diagram and a canonical forms of STD space representation. Assume I'm given this transfer function. I want to see how can I calculate the matrices for the STD space representation. Okay. The main form of the representation is known as a control canonical form. How I can calculate the matrices for the canonical form? Let's look at it this way. Again, we isolate the dynamic of the system through integrators. How? I'll let you know. The main feature of this structure is that each state variable is connected by the feedback to the control input. Okay, so each state is given as a feedback and added to the control input. How? Let's see. I have a second order system. Look at the characteristic equation. S squared plus 2s plus 7s plus 12. I have this second order system. If I have second order system, I need two integrators. So we connect these integrators together because they are a state of my system. I define the input of the first integrator as x.1 and the output is x1, and the input of second integrator x.2 and the output is x2. Here x1 is equal to x.2 or x.2 is equal to x1. Okay? Now I need to take feedback from each state, x1 and x2. Look, in reality, each of these states have a physical meaning. For example, if you have the dynamic system, x dot 1 is acceleration, x1 is displacement, velocity, x dot 2 is velocity, and x2 is displacement. Okay? And you can measure each of these states by a sensor. For example, if you have rotatory velocity, you need a tachometer to measure that one, and if you have the rotary displacement, you need a encoder
If we can't use observers.
or
right?
potentiometers. What?
If we can't, we have to use
Okay, if we can measure it, we have some ways to, if we don't have proper sensor to measure these states, we have some advanced mathematic approach to reconstruct that signal, but it's beyond this much. Don't worry. So, after defining the states, look, ys over us is this transfer function. So ys is this transfer function multiplied to u. The input is u. I get 2 feedback minus 7x1 minus plus 7 and plus 12 minus 12. Look, I get the feedback from each state, and the output is the negative coefficient of each order of integration. If I add these two to u and define s, look, s is x1 and 2 is x2, the output of the second integration. If I add these two blocks, sorry, this one is 1. This one is 1. Here is 2. 2x2 will build up out. So to make sure it is correct, let's see. Again,
So,
yeah.
why is it now -7 and -12 rather than?
This is the way we represent. We take the feedback. It's a negative feedback, isn't it?
Okay.
But I assume all is positive. So I put the negative here. It's a negative feedback, isn't it?
Yeah.
So, but I have all positive here. I just bring the negative here. Okay, in order to have negative feedback.
Okay.
It's not a big deal. But it's not important. What I want to show you how to build up a transfer function using a set space representation. I'm looking for a tissue. Anybody has tissue here? Okay.
Which one does this refer to?
because like he screwed up and was looking at the area.
Which is? Which one?
It is about this
Oh, that is.
Okay, everyone. I want to see if this block diagram is the correct one. Look, I want to build up this transfer function using this block diagram. Y is equal to 2x2 plus x1. And if you look at here, x dot 1 is equal to minus 7x1 minus 12x2 plus u. X dot 2 x2 is equal to s x dot 2 and x1 is equal to s x dot 1. X dot 1 is given here. S minus 7x1 minus 12 x2 plus u. Two x2 plus x1. 2x2 plus x1. So I have x1 here. And x2 is equal to sx dot 2, which is equal to sx1. Correct? So it will be equal to 2 sx1 plus s minus 7 x1 minus 12 x2 plus u. Okay? If you substitute, I don't have time to go further, but if you do this calculation, you need to just have y and u in your relation. You need to get rid of x1 and x2. Based on this block diagram, if you do that, you will get the same transfer function. Please do this calculation at home by yourself. If I had time at the end of the module, I will. Let me see. Let's do calculation for you. So, this is, let's do this way. Sx1 minus 7 x1 minus 12 x2 plus u. And if we do that, 2x1 y will be 2. S minus 7 Yes.
Could you write this one bigger, or write the dots a bit bigger, please?
Okay, sure. So, I think it's better to do it by yourself at home. Let me do it bigger. Okay. Look, what? Let's start from. Y is 2x1 is x1 plus 2x2. This is the relation. And let's start from here. x1 is equal to sx dot 1, which is equal to minus 7 x1 minus 12 x2. This is x dot. Oh, sorry, I made a mistake. Here is 1 over s. Here is 1 over s. Minus 12 x2 plus u. And x2 is 1 over s, x dot 2, which should be equal to 1 over s, x1. So, x1 is equal to 1 over s minus 7 x1 minus 12 1 over s x1 plus u. So I bring all x1 here. I have, if I get the common denominator, I have 1 over s squared minus 7 s x1 minus 12 x1 plus s squared plus su. So s squared minus 7s plus 7s plus 12 x1 is equal to su. So u is equal to, x1 is equal to s over s squared plus 7s plus 12 u. And x2 is equal to 1 over s x1. So will be equal to x dot 2 is equal to x1. So if look here, I have the s squared plus 7s plus 12 plus 2s squared plus 7s plus 12 multiply to 1 over s. This s will be cancelled out with this s, so y will be equal to s plus 2 over s squared plus 7s plus 12 u. Look, I get the same transfer function. Okay. We build up here. Y here is 1. Is a typo here.
Oh, okay.
Is 1. Y is 2x2 plus 1x1.
Yeah, it's fine. It's just because of the.
What? Okay.
Do we just use the block diagram when it's in S form already?
Pardon? Look, what I've done so far, I'm given a transfer function. Based on the order of the characteristic equation, I define two integrators. Because I have second order differential characteristic equation, so to begin, I start with two integrators. Output of each integrator is my state. And I give a negative feedback to the first integrator plus the input. So here I built up my characteristic equation. Each each zero or each coefficient of the denominator is the output of the same integrator. I have s, the s is here, and I have x2, which is the output of the second integrator. We'll build up the whole transfer function. But no worries, if you're not about sure how I deal with it, I will explain to you in easier way. But before going further, if you look at here, x dot 1 is my first state and x dot 2 is the second state. If I look at this relation, look here, x dot 1 is minus 7x1 minus 12x2 plus u. Isn't it?
Yeah.
So, if this is the case, the highest order of differential equation is x dot 1 equal to minus 7x1 minus 12x2 plus u. And the rest is given. X dot 2 is equal to x1 and x dot 1 is here. And the output is x1 plus 2x2. If I form the canonical form or find the matrix transfer input vector and the output vector, FC, the FC stands for the canonical. Will be minus 7, minus 12, 1, 0, input 1, 0, H, 1, 2. Very easily. If you have the given transfer function, the matrix, system matrix, the first row is the negative coefficient of the characteristic equation. The matrix G is 1, 0, whatever. And H is the coefficient of your denominator. So if a transfer function is given and they ask you what's the S-space representation, you just need to look at the coefficient of the characteristic equation. Based on the coefficient of the characteristic equation form the first row of your system matrix, the rest will be diagonal 1, 1, 0, 0, 0, 0, 1, whatsoever, and the input vector is 1, 0, and H is the coefficient of denominator. In general form, two significant things they explained. The coefficient 1 and 2, which are the coefficients of a denominator, build up your output vector HC, and the coefficients of the denominator will build up your system matrix So in general case, if you have transfer function in this form, if you're given this transfer function, you need to, if you want to convert the state space format, canonical state space format, it will be in this form. The first row are the negative coefficient of denominator. The rest will be 1, 0, 0, 0, 0, 1, 0, 0, 0, and at the end 0, 0, 1, 0. The input is 1, 0, 0, depends on the dimension of your system. And xc is b1, b2 to bn, and gc is 0. Okay, the easiest way to convert. What's the drawback with this representation? What? Is any drawback with this representation? What? Say it loud.
Complex.
Is what?
Complex.
Converts?
Complex.
Complex? Complex of what? The reason is that the output is summation of your inputs. Okay, if you want to implement real time, you need to have feedback of all your sensor, all your states, which is not the case. Most of the time, the output is just one state. While using the canonical format, it will be combination of the all states, the output of the system, which is not desirable. But again, this is not the only way we can transfer to the state space representation. An easier way is that if we use the partial fraction to find the poles and build up the block diagram using this partial fraction representation. Look again, ys is 2 over s plus 4 u minus 1 over s plus 3 u. The input is u. Using one integrator, I build up the first fraction. X dot 1, 1 over s x1 minus 4 will build up this one. And the output of this feedback multiplied to 2 will build up totally this fraction, the first fraction. In the same way, u is the input to the second fraction. I define the second state, x dot 2 and x2, minus 1, the denominator of the second fraction. The sum of these two fractions will give me the output y. So y is the summation of both feedback. If, again, I represent this state space in the standard representation, I will have minus 4, minus 3, 0, 0, gm 1, 1, hm2 minus 1, and gm 0. Here I have a better format for the fm. If you look at this one, diagonal of this matrix is minus 4 and minus 3, which are the poles of your system. Okay? Diagonal matrix, which elements on the diagonal are the poles of the system. Gm is the vector, the unit vector, and hm are the coefficient of the or the fraction of the coefficients of each fraction. What's the problem with this approach? If you have a complex conjugate poles, it's not easy to represent in diagonal of the matrix. There are some other ways, but it's beyond this module. I just want to give you the M here represent the modal canonical forms because I have the poles in the diagonal of the system matrix. The poles in the state space formulation or representation are known as the normal modes of the system. So normal modes and pole location are the same definition for the system characteristics. Okay. Is any question? 5 minutes more. I will finish. Any questions so far? So now we know how to convert the given state space to transfer function, given transfer function to a state space format. How about if I given a state space representation, how can I convert it to the Laplace, or how can I find the related transfer function? Look at this again, differential equation or a state representation. If I want to solve this differential equation, first order differential equation, how can I solve this first order differential equation? First, what's the response of the first order? What shape does it have? A first order system? Exponential. Exactly. Very easily you can solve it. For example, if you have the third order system, you can solve it by this vector as an exponential response. But in order to solve this differential equation, I need to use Laplace transform. If I get the Laplace transform of the first differential equation, I will have Sxs minus x0 initial condition equal to fxs plus gus. Correct? If I bring x of s to left side and keep us in the right side and factor at x of s, I will have si minus f x of s equal to gus plus x0. What's I here?
Identity matrix.
What, yes, identity matrix. Why do I have identity matrix? X of s is a vector. F is n by n matrix. If I want to factor out xs here, it's si. Do you know what I'm talking about? Okay. Look, I have, for example, 1, 2, 3, 0, x1, x2, plus or minus x1, x2. If I want to factor out x1, x2 from this relation, how can I factor out? I need to factor out this one, and here is the identity matrix. Correct? For example, you have 3x minus x equal to 0 or equal to whatever. If you factor out 3 minus 1x, isn't it? Because you have a matrix, it will be identity matrix instead of 1. So you have si minus f x of s equal to gus plus x0. If I want to solve it for the xs, I need to multiply to si minus f inverse to find x of s. So x of s will be equal to si minus f inverse gus plus si minus f inverse x0. Correct? Again, if I get the Laplace transform from here, y equal to hx plus gu, I will have, there is no differentiation. Ys is equal to hx of s plus gus. If I substitute x of s in this relation, y of s will be equal to h si minus f inverse gus plus h si minus f inverse x0. H si minus f0 is x of s. Sorry. Si minus f inverse. Okay. So I have ys and I have us. If I want to find transfer function ys over us, how can I do that? What was the main assumption for finding the transfer function? What was the transfer function definition? What?
Steady state.
No.
All the initial conditions are zero.
Are you talking about? Are you talking that?
Yes.
Okay, that's correct one. That's correct one. Yeah. The transfer function is the ratios. Yeah, you need to celebrate that one. Transfer function is the ratio of output over input when your all initial conditions are 0. So I put x0 equal to x0 equal to 0, and I can find the ratio of y over s, which is given as h si minus f inverse g plus k. So if you first shape the SLS space representation, okay, using this relation, you can directly find the Laplace, the transfer function, Zs over Zr. Okay, so I think that's enough for today. I will give you a solved example next week. Any question? More than welcome, come to my office.